That's fair. First of all,
Recording in
here,
progress.
you don't need to understand what these Fermi levels are at all. We don't need
Yeah, so really, I mean, actually, even now, after taking a bunch of quantum where you derive these things and doing all this, the idea of a Fermi level and Fermi's golden rule and these other things that relate to semiconductors are a little unclear. So it is not, so Fermi level, don't worry about that. What I want you to understand is that in conductors, a bunch of electrons sit in what we call the conduction band. They're just freely floating around, bouncing around all the atoms there. In insulators, they're mostly sitting in the valence band, where they're all stuck to the atoms in the lattice. Because in general, materials are a lattice of elements. You have an element there, an element there, and it's like a grid, and the electrons are stuck in place in that grid.
let's
Okay,
go what he's talking
but
about.
depending on how close those bands are together, you can have some electrons that jump from being stuck to being able to freely float around. Being stuck is the red, and being able to freely float around is the blue. So in insulators, it's really hard to make that jump because the energy jump is really big. But in a semiconductor, just like the room temperature is enough heat that'll let some of those electrons jump from the valence band to the conduction band, from being stuck to being able to freely float around and bounce around. Yeah, is there a question, Naman?
Yes. Um, so can you go to the that airline food slide?
Yeah, I
Yes.
think Jay's gonna explain that now before I interrupted him, so I'll let him talk.
Yeah.
Oh, okay. Because I was asking why are there so many layers? Is it just ensuring safety, or can the shock travel through just the insulation point?
So the lead sheath, bedding, and armoring are basically to give the wire some structure for the most part. Really,
Okay.
the essential components are the conductor and then the insulation.
Okay. So the
Fancier wires will have more layers.
insulation is usually enough to stop like
What's the deal
uh
with airline fruits and semiconductors?
so um
Because
so is
airline food is terrible.
is the insulation just usually enough to stop a shock from coming from the conductor side?
Yeah, so yeah, short answer is yes. That you're right.
Okay. Yeah, I'll explain more. Sorry. Slide. Okay, so let's kind of just break down what's going on here. We have our conducting wire just going straight through, and we have our insulation going across. And the entire point of insulation is to always block electrical supply going through it. It will always block it, and as long as insulation is strong enough, then there won't be anything going conducting through it. And the conductor, same thing, but the opposite. Electricity will always conduct through the conductor, and again, no way to control it. Semiconductors are different. There's no control here. We have properties of material that are entirely set. Whereas semiconductors, we have, I think it's here, we can dope our semiconductors, in this case silicon, with other elements to tune the electrons floating around and thus tune the properties it has, which is why it's so important and why it's used in electronics everywhere. Okay, yeah. So let's just quickly get into what I mean by doping. So doping is just adding a small amount of a different element into your larger element. So let's say we have silicon here. When I say doping, I just mean adding a small amount. So let's say we intersperse like a very small concentration, I guess, of phosphorus. What we're actually doing is n-doping our silicon. We're introducing an element which has more electrons than silicon does. So there's more electrons in the element than in the sample than there normally is. And you can see here, phosphorus, arsenic, antimony are going to be our n-type dopers, because I'm not too sure how familiar you guys are with the periodic table, but as you go right, there's an extra electron on the outside. So there's one more electron added. That's our n-doping. P-doping is the opposite. Aluminum, gallium, indium, and boron, these all have one less electron. And this one less electron just kind of eats up or takes away electrons that normally exist. So you see that, I guess, yeah, group 3. We didn't have the group here. You don't have to worry about the group numbers. All you have to really worry about is with silicon, there's elements with greater electrons, elements with less electrons. Less electrons means it's p-type. More electrons is n-type. And what I mean by p and n is negative and positive. So p-n junction. We'll get into p-n junction in a second, but I think a good kind of way to remember this is that, yeah, soon, but yes, okay. Yeah, a good way to remember this. The wording for N and P, it might seem like, oh, there's a positive and a negative charge on the kind of sample you have, but that's just not true. So with all of these, we have to remember it's not charges, it's not like a cation or an anion or anything. It's just there's more or less electrons, and since electrons are negative, N type means it's negative, P type is positive. But I want you guys to really just remember, as N is just elements that have more electrons and P is elements with less. I'm stressing this point a lot because it's important for me to go later. And I think Ishaan has something to say about that as well.
Yeah. So how I like to think about this, because when I first learned this, it was pretty confusing. The doping elements, so if I have an array of silicon, my semiconductor, when you when you go to synthesize a new circuit and fabricate it, you get basically this slab of silicon, very, very ultra pure silicon. And your job is to basically use that silicon and make a circuit out of it, a very minuscule nanoscale circuit. And when you dope that silicon, what you're doing is you're basically introducing elements that are trying to pretend to be the other elements. So if I dope it with phosphorus, the phosphorus is going to put on a mask and say, hey guys, I'm silicon, but it's just carrying around another electron with it. And so when you put it into the lattice, like this diagram shows here, it's now pretending to be silicon. So it's a phosphorus just sitting in there doing the same thing silicon would do in the lattice, but it has an extra electron that's now going to float around and be a freely floating electron. In the same way, if I introduce boron, a group 3 element that is lacking an electron compared to silicon, it's going to pretend to be silicon in the lattice, but it's actually going to be missing an electron, and it's going to be a hole. So a hole is like a bubble in water, right? A bubble is just like a hole of, it's like a little bit of air that floats around in water. A hole is like a bubble, okay? And that hole is mobile in the same way that a bubble is mobile, okay? So I just wanted to say that to you, Jay.
Yeah. So holes and then bubbles. Yeah, that's good. Okay. So let's just do some quick testing here. I guess just private message me this time. Try not public message because I want everyone to get the good practice. Just private message me in chat if you introduce antimony into silicon. Are you N doping or P doping your silicon? Let me see if I can get chat to work properly. Okay, I'm seeing some answers now.
That's a good question, Water Cup, whoever you are. The reality is, so you you can, I very cautiously say this, you can in principle dope with that, but remember what doping is trying to do. We want to dope with an element that very closely emulates silicon, aside from the fact that it has an extra or lack of electrons, okay? If you dope with something that has two less or two more electrons, it's not gonna emulate silicon very well. Why silicon? So as you probably know, carbon is the element of life, right? It has four valence electrons, and carbon is everywhere. Um, there's certain properties, and I say that cautiously, that silicon has that also make it very conducive to building things. It basically it has very tunable properties. It's basically like right in the middle. The max number of valence electrons you can have, roughly speaking, is 8 for these things, and silicon is right in the middle. It has 4. That begs the question: why not carbon or germanium or tin? And I can't really answer that briefly.
That's a
but
very chemistry question. Why silicon? If you end up taking like a pretty advanced chemistry class, you'll get the answer. But yeah, there are other elements that we as in like I guess like semiconductor engineers will use, but for the sake of an electronics class, we're only going to look at silicon. But yeah, you can kind of see with the coloring here. I don't really know what to call that color, but the one that's not green or blue, or I think like brownish color, is going to be your semiconductors in some capacity. Yeah, metalloids, I think is what you guys would call it. Yeah, so these all have semiconducting properties. Okay, let's just, I see many of you guys have answered. I'm not going to give any more time. Yes, that is N-type. So, and you're introducing electrons. Great. Okay, let's see if I can avoid clicking. There we go. Okay, guys, answer these next. Should be pretty simple because this kind of tells you the answer to that one. So I see some answers in the chat already. I think we'll just go on. Yeah. So anything left to silicon here, we see your aluminum, gallium is going to be a good p-type doper. I think for this class, we're probably going to discuss gallium, right?
Actually, boron is really the major p-type dopant
Oh,
because
really?
remember, so as Jay said, the orange elements in this diagram are metalloids. I
Oh,
say that
yeah.
cautiously. So these are those elements that, for wacky and wild reasons in chemistry, have desirable properties that are nicely tunable. The elements in green are a little too metallic in nature, and the elements in blue are a little too gaseous in nature. That's a very poor explanation that an actual chemist would get mad at me, but you can think about it like that.
Okay. Oh, yeah. We're on. Okay. Oh, yeah. Good answers, guys. Good answers. Okay. Important question. Private message me this one. What is the net charge? So I'm seeing some people with the right answer, some people with the wrong answer. It's fine if you have the wrong answer. It's okay. But the answer is not -1. It is, in fact, 0. Remember, when I said that you're introducing more electrons or less electrons, you're also introducing more protons as well when you're doing this, or removing more protons. So you don't have to know chemistry to fully understand that since you're changing the actual elements and none of our elements we're adding are charged, the resulting material is not charged. I think that's the best way to kind of think about it. We're not introducing charges, we're introducing elements that are similar to silicon, but with slightly more electrons and protons, slightly less electrons and protons. So I think that's for this one. If you don't have any chemistry background diseases, just remember that it is neutral. And
so the key idea is that when we dope a material, we're taking that grid of elements and we're just plopping in some extra elements into there. Okay? And when we dope it with an n-type, the extra elements that we plop in happen to also give us some extra electrons that can float around. When we dope it with a p-type, that extra element that we plop in happens to also make it so that there's kind of bubbles or holes or lacks of electrons floating around. Okay? But the actual element that we're adding still has protons and stuff and still has electrons and stuff. So the net charge of that material is still neutral. And it's very important to remember that. The p-type material and n-type material are normally still electrically neutral, even though there's some free-floating electrons and free-floating holes in the material. So
I think you can...
I can steal the screen share from you.
Yeah. Oh, did we just start recording or no?
Yeah, I started recording a little late, but it is recording now, so.
That is fine. It's
okay. Okay. So now that we've established what a p-type and an n-type material are, this kind of begs the question, what happens if I put them next to each other? Okay, something really interesting happens. So let's go step by step here. It's really hard to wrap your head around at first, but the more you think about it, the more it'll make sense. So the n-doped side, the side on the right here, has extra free electrons, okay? And the p-doped side has a lack of free electrons. And we model that lack of free electrons as positive charges that move around, okay? That's not actually what's happening, okay? What's happening is that the lack of an electron is moving around. That's why I tell you to think about it like a bubble in water. The bubble is like a lack of water that's moving around inside of water, okay? So the n-doped side has extra free electrons, and the p-doped side wants those free electrons, right? So it's going to donate those electrons. It's going to move them over. But as those negative charges fill the bubbles, you can think of the negative charges like water droplets in air, and the positive charges like bubbles in water. As the water droplets in air fill the bubbles, what you end up with is what is effectively an electrically neutral region, okay? The negative charges fill up the positive charges. We call this charge recombination, actually, because physically, the negative charges are literally recombining with the holes and filling them up. And so that depletion zone is completely neutral. There's not a bunch of free-floating negative charges, not a bunch of free-floating positive charges or holes. There's nothing free-floating. And so this depletion zone is completely insulating. No current can flow through that depletion zone. Okay? The electrons leave behind positively charged atoms on the n side. And now here's the hard thing. Here's the hard way. And yes, so I'm really glad you said that, Aiden, because that's wrong. That's the easiest misconception to make when we think about p-n junctions. It is because that's what it sounds like. N negative, p positive, right? And that's true for the material. As in N has negative charges that are floating around, and P has positive charges that are floating around. Okay, Veritasium does have a very good video about this, I think. Yeah, so empty seeds, bubbles, similar thing. But once these charges migrate, once the negative charges migrate out of the N side, now the N side has actually become charged. It's lost some of its negative charge, but all the positive charges that are fixed in the lattice remain. And so actually, since we've lost some of the minuses on the N side, we've accumulated a net positive charge here, an actual real net positive charge. And since we've lost some of the pluses on the P side, we've accumulated a real, very true negative charge. Okay? That's kind of counterintuitive, right? So we call it N side, but actually, once the charges leave it, we're left with the positively charged material. And we call it P side, but once the positive charges leave it to go to the depletion zone, we're left with a negatively charged material. And if you think back to lecture 1, an electric field flows from positive to negative net charge, okay? So now we have this electric field, I'll draw it, that's pointing in this direction, okay? Because remember, although we have free-floating electrons on the N side, we've now accumulated a net positive charge here, to draw that, and a net negative charge here, okay? Since we have a net positive charge here, that's going to try to keep pulling the electrons back in. And so eventually, this depletion zone will grow to a size after which it can't grow anymore. Because the electrons, this positive charge keeps growing, and so it's going to keep pulling those negative charges back in. In the same way, this negative charge keeps growing, and so it's going to keep pulling those positive charges that are trying to leave back in. Okay? So here, it's neutral. Both sides are electrically neutral, even though there's free floating charges. Neutral. But here, once the charges move, the two sides become electrically charged. The depletion zone is like a separation zone. Yes, that's a good way of thinking about it. Current cannot flow through the depletion zone. It can through tunneling, quantum tunneling processes, but really, for the most part, we think about the depletion zone as where current can't flow. Okay? So the depletion grows to a size, and actually with some equations and a bit of sophisticated physics, not that sophisticated, but somewhat sophisticated, we can calculate what the size of that depletion zone will be, like the actual size in nanometers, I guess, micrometers maybe. So let me be just completely, extremely, overly explicit about what I'm saying here. Normally in the N-type material, the electrons are floating around like a water droplet on a table in air, okay? And normally in a P-type material, the holes are moving around like bubbles in water, okay? In the depletion zone, the electron has combined with the hole, okay? So these electrons from the N side have migrated to recombine with these holes, which are lacks of electrons on the P side. And that creates a zone where there's no free-floating charges, okay? In the middle. But what it also creates is a positively charged N side because some negative charges have left there, and a negatively charged P side because some positive charges have left there. Okay? So remember, there was no net charge on either side originally, just free electrons and free holes, water drops on a table and bubbles in water. But they recombined and left us with net charge on each side that created an electric field that opposed further expansion of the depletion zone. Does this make sense? This is like the most important thing, and it's just super weird to wrap your head around, okay? No? How can I make it make more sense for you?
I think the diagram is what's like confusing people because it's showing its positive and negative charges. But I want you guys to remember that the positive and negative charges that the diagram is showing aren't actual real charges that exist in the material. This is more like you can think of the negative as actual electrons, and the positive you're going to think of places that the electrons are trying to go to. I think is the best way to describe it. So if you want
So
to
what Jay said is exactly right. I think I should have emphasized that more. So these are real electrons that are floating around, but the material itself is still electrically neutral. Like there's still basically fixed positive charges in the lattice here that are neutral relative to this. Actually, I have a really good diagram in a textbook. Let me find that diagram because I think that'll be helpful. So just give me 1 second. In the meantime, does anyone have any questions that
I can help answer
don't
any other questions that
require
you guys might have.
diagram?
Okay, Omar, what's up?
Wait, since
you
I
guys-
was late, since I was late, were you guys talking about like LEDs and PN junctions like that? Like how LED works? Or
We were
like
talking
PN
about the
junctions.
basis of
Oh,
what
okay.
semiconductor is, like more
Right.
like physics. Yeah.
Okay, so this book is a little too complicated for what. Do you guys see my screen? Is it all
Don't
fine?
get freaked out about what's on the screen right now, guys. This is all college level stuff.
Is it? No.
I think I just will note that the actual explanation for this in like a more concrete way does require a lot more physics knowledge. So what we're kind of showing you guys now is, I think
So this diagram perfectly illustrates what's going on. On the N side, okay, this kind of sucks actually. See, the other thing is the explanations for most of this kind of suck in most diagrams. Okay, here's a good one. So ignore like most of the words on this slide, on this image. What I want you to see is kind of low quality, but the positive charges on the N side are fixed in place, okay? These are positive things that are just stuck. They are nailed down to the table. And on the P side, the negative things are nailed down to the table. But those minuses are free to float around on the N side. So the N side as a whole is electrically neutral, but the minuses can float around and the pluses are stuck. On the P side, the minuses are stuck and the pluses can float around. Okay? So from the N side, the minuses migrate into the depletion side and the depletion region. And from the P side, the pluses migrate into that depletion region. Okay? And so what we end up getting is pluses that are fixed in place and minuses that are fixed in place in the depletion region. Okay? And as a result, what now happens is that since we have less minuses than pluses here, because the free-floating minuses have moved away, but we're still left with all the pluses that were nailed in place, the N side has become positively charged. And for the same reason, the P side has become negatively charged. And that forms an actual electric field that prevents further expansion of the depletion region. So the depletion region expands without any applied charge to some fixed width. Okay. Does that make any more sense? Does that diagram help? That's good. Okay.
If anyone is confused, message me in chat. I'll try and answer it with a way that might be like better for a specific person.
Okay.
Fine.
So
this is
now,
a confusing concept, so it's good you guys.
Okay, this stupid thing is stuck. Let me just stop my screen share for a second and restart it. So now we're gonna get into what this actually means and why we're even talking about this. What happens if I connect my PN junction to a battery? Okay. So in general, let's think about what high voltage does. If we think back to lecture 1, a high potential, a high voltage pushes away positive charge and pulls negative charge, right? So the positive side of the battery pushes away the holes and the negative side pushes away the electrons. Okay? Now remember, on this side, the bubbles drift towards the junction from the P side. So inside this depletion zone, things are fixed. Sorry, not there. Inside this thing, the charge carriers are fixed in place. They're nailed to the table. Okay? When we apply this positive voltage, we push the holes into the depletion zone. And as a result, we decrease the size of the depletion zone. Okay? For the same reason, the negative side pushes the negatives into the depletion zone. And we decrease the size of the depletion zone. Okay? If the voltage is strong enough, we end up decreasing the size of the depletion zone to be really, really small, so that currents can now flow through the PN junction. Okay, we allow current. But what if I attach the battery the other way around? What if I attach the plus side to the N side and the minus side to the P side? Okay. Now the P side is going to have the holes pulled away. Okay, because the minus is going to attract those pluses. For the same reason, the P side is going to have the minuses pulled away from the depletion zone. And so we actually expand the size of the depletion zone here. And expanding the depletion zone means even less current can flow. Okay? So we're explicitly disallowing current here. Current cannot flow through this PN junction. And so we've created a device that only allows current in one direction. Okay? And so if you're confused about everything I'm saying here, let me kind of pull everyone back in with this slide, okay? So in the depletion zone, what we've created is an electric field that points with these arrows, okay? Now, when I have a battery that applies an electric field in the direction shown. It applies it in this direction right here. If I take those arrows and move them into here, those arrows point in this direction, and that decreases the size of these arrows. So that electric field becomes much weaker, and the size of the depletion zone decreases. Okay? For the same reason, if I have the electric field applied in the opposite direction, I increase the strength of the electric field in the depletion zone, and I increase the size of the depletion zone. Okay? Because remember, that's what this direction of this arrow goes. So the moral of the story is, when I apply a positive voltage to the P side of a PN junction, I allow current to flow. When I apply a positive voltage to the N side, I prevent current from flowing. So we call this forward bias because it can flow forward, and we call this reverse bias because it can't flow. We're trying to make it go in reverse, but it doesn't do that. So let's kind of abstract away from the physics and let's get to the electrical engineering, the actual circuit side of things. A PN junction is basically the simplest possible diode. A diode is a device that only allows current in one direction. Okay? And that direction is the direction that this circuit element points. In particular, it's from the anode to the cathode. Those terms don't really matter. What matters is that current can only flow in this direction. Current cannot flow in this direction. That can't happen. But this can.
So is it basically a DC current?
It could be AC. It could be changing, right? But it can only be in one direction. Actually, one of the most important applications of diodes is if I have an AC voltage source and then a diode right here, and then some load, some resistor, and say by voltage sources like this over time, if I put the diode there, what I'm going to deliver, so this is the source, it's called a rectifier. Instead of delivering the negative part, I'm just going to deliver this, right? Because only the positive part gets through. Okay? And that's important for devices that can't have voltage flowing in the wrong direction, otherwise you'll break the device. For example, a lot of ICs, I think, integrated chips on circuits can be damaged by having strong negative voltage applied to them. A rectifier is a rectifier is an important part of converting AC to DC. Yeah, so a bridge rectifier is something that looks like, I might be wrong about this, I'm just from memory, something that looks like this, I believe. And what this does, so think about what this does, right? We allow the positive part here, and then, anyways, I'll put some of these on the problem set, actually. I'm not going to go into this too much now, because we have some simple examples that I want to go through first before we talk about more complicated rectifiers. It's not a Wheatstone bridge. A Wheatstone bridge is a resistive thing. Don't get mixed up with that. Wheatstone bridge is just it's a combination of 5 resistors. So it's not a Wheatstone bridge. Although I think a Wigton bridge can be used to rectify voltage, if I'm not mistaken, but a diode is a more robust way of doing that. But let me
Anyway,
get back on topic
everything
here.
that he just said, you do not have to know if you're scared about
Yeah,
what he's talking about. This is
I'm just
much more
yapping a bit about some questions I saw. But you're asking good questions. I mean, rectifiers
good
are
questions,
a
yeah, but
very important application of diodes. We are going to do an activity. Well, it'll be the course challenge in a second, but yeah. So real world diodes have a curve that describes their voltage drop versus current. So an ideal diode simply blocks current in one direction and fully allows it in the other direction. So if I apply a voltage in the wrong direction, it gets fully dropped. It gets completely canceled out. If I apply a voltage in the right direction, the diode just acts like a wire. It's like it's not even there. Okay? So are diodes like valves in the heart? Yes. Yes, you can think of that. Because valves in the heart don't. Well, as I am a biochem major at Purdue, but my anatomy sucks. So I'm gonna say yes, but I could be wrong about that. So, but yeah, I think that's right. Um, Diodes leak. Yeah, there's a bit of leakage current. So this is on the left is the curve for a resistor, V equals IR. It's completely linear, right? We increase voltage, we increase the current to the resistor. You can think about diodes like a resistor that just kind of sucks at doing its job. When the V is negative, there's no I is 0. Actually, I can be a little bit negative because maybe some current can get through that depletion region, but it just leaks a little bit. So that curve might just be a little bit negative, but it's close to 0. So when it's a little bit negative, that's the leakage. But when V is positive, I can get through, and there's equations that we use to describe that. Ideal diodes don't leak. Yeah. So let's do a quick chat. Interactive. Finally, you guys get to speak and not hold your peace. Okay. So let's assume an ideal diode here. Current flows freely when a positive voltage is applied, and zero current flows when a negative voltage is applied. So for the circuit on the left, how much voltage is dropped by the diode and how much voltage is dropped by the resistor? For the circuit on the left, how much voltage does the diode drop and how much voltage does the resistor drop? And people should give it a go. Anyone? Anyone got to venture a guess? Come on, we got 55 people here. Someone can guess. So yeah, the diode drops 0 volts, okay? Because since we're applying 5 volts to it, okay, it's in forward bias. And so current basically freely flows, like the diode doesn't even exist. It's like it's just a wire here. And that means how much voltage does the resistor drop? 5 volts, exactly. Had to drop the rest. Kirchhoff's voltage law still applies. There's nothing special here that makes Kirchhoff's voltage law not apply. Now what about the circuit on the right? Ground is just a reference. It doesn't matter where I say ground is. Ground is just reference. So for the circuit on the right, how much voltage does the diode drop? The diode drops 5, and the resistor drops 0. Exactly. So, because here, no current is flowing, so the resistor can't drop any voltage, and so all the voltage has to be dropped by the diode. Now here is probably the most ubiquitous application of diodes. The reality is OR gates in practice are made with transistors. It's a simple, I think, dual MOSFET circuit, but we'll talk about that later. A simple OR gate can be constructed with this. So we're going to go into the binary realm now. Inputs A and B can only be 5 volts or 0 volts. There's no in between. They're only high, like a binary 1, 5 volts, or low, a binary 0, 0 volts. Okay? So if A is 5 volts and B is 5 volts, what is the voltage across R3? Not 10. So remember, they don't add. If this is basically wire, right? If we just model this as wire, we basically have 2 points, 2 wires that are touching, and they have the same voltage. If they had different voltage, this wouldn't even make sense. Like this can't be 10 volts and this be 5 volts, which is why I said they can only assume 2 values. Okay? This is not possible. You can't have 2 wires that are touching each other and have different voltages. That's not a thing. But yeah, the right answer is 5 volts. Now, what if A is 5 volts and B is 0 volts? How is it 5 volts? So if A is 5 volts, this diode is in forward bias, so it's basically a wire. If B is in 5 volts, this diode is also in forward bias, so it's like a wire. And that means we have a wire that's connecting 5 volts to this point right here above the resistor. So this point's also 5 volts. So if A is 5 and B is 0, so if I have B is 0 volts, I guess I should say, maybe instead of 0 volts, let's say B is negative 5 volts, okay? So we're applying negative voltage onto there. So if B is negative 5 volts.
Wait, is there such thing as negative voltage?
Yes. Because remember, voltage is all defined with respect to a reference. I could say ground is actually negative 1,000,000 volts, and then I just have to do a bunch of math of negative numbers, and
Oh, okay.
annoying, but the physics is all the same. So it is indeed 5 volts. So input B, this is completely blocked off, okay? Since we have applied a negative voltage to the diode blocks that voltage, okay? But here, 5 volts is just connecting that wire, and it connects down to there, so it's 5 volts there, okay? Here it's like there's a break in the circuit. It's like input B it doesn't even exist anymore, okay? It's negative 5 because we've just set it to that value. I have a magical device that makes points whatever voltage I want them to, okay? Now what if A is 0 volts and B is 5 volts? And instead of 0, say it's negative 5. Say that's negative 5. Say that's negative 5. Okay? It's the same thing, except in this situation, A is completely blocked off, so this is like completely separated from the circuit, because that's negative 5, and B acts like a wire, because that's 5. Okay? So now the 5 volts connects to there, and we're at 5 volts here. Now what if both of them are low, as in negative 5 volts? So again, not 0, say it's negative 5. So this is negative 5 volts. This is negative 5 volts. The answer is 0. We're completely blocked off here, and we're completely blocked off here. We're not putting any voltage into here, and so it's just going to be 0 volts. And so what we've created is a thing that says if A or, keyword or, B is 5 volts, then R3 receives 5 volts. If neither of them are 5 volts, then R3 receives 0 volts. That is an OR gate. It is a logic gate. And it's the first bit of binary digital logic that we've seen. So the problem is, what if I wanted to get you to make an AND gate? So an OR gate has a truth table like this. We typically model it like this. So like if A is input A and B is input B, if A and 0 are both zeros, then we get a 0. If either one of them is a 1, then we output 1. Okay? That's the same thing that we did here. If A or B is 5 volts, then we get 5 volts here. But if neither of them are 5 volts, then we get 0. Okay? Is there a simple definition for the superstring theory? I'm not even going to talk about that. I don't know. No. Now the problem is, what if I wanted to make something like an AND gate? I can't make this. You can't make this with only diodes. And the reason is a diode cannot output a low value. It can only output a high value. It outputs a high value or nothing. But to make an AND gate, I need to be able to output an actual low value. Okay? Yeah, so not A or not B is in fact an AND gate. Just from I think it's De Moivre's theorem. Is that what it's called? De Morgan's theorem? I don't know, something. But again, that's not an effective implementation of an AND gate, and we actually can't make that with only diodes. You can try, and if someone sends me a working implementation of an AND gate with only diodes, feel free to collect your Nobel Prize. Yeah, Omar?
There's also something called a NOT gate.
True. Again, yes, you're exactly right. So a NOT gate has a 0, and if it takes in 0, it becomes a 1. If it takes in 1, it becomes a 0. But the key right here is that we need to be able to take in 0 and output 1. With a diode, I can't do that, right? For a diode, if I send in 0, I get out 0. If I send in 1, I get out 1. I don't have any way of sending in 1 and getting out 0, or sending in 0 and getting out 1. I can't make a NOT gate with just diodes. So, as we'll see on Monday, the solution to that is transistors. Transistors solve that problem for us. Okay. Oops. Oh no, I showed the. Okay. Well. So let's have a quick check on this. So suppose inputs A and B can only be 0 volts, say -5, just to make it even more clear, -5 volts or 5 volts. Under what combinations of A and B does R4 have 5 volts right here? Okay. So there's 4 combinations: A high, B high, A high, B low, A low, B high, and A low, B low. So which of those 4 combinations do we get 5 volts right here? A low, B high is one. Anything with B high? So yeah, the answer is indeed anything that has B high. The reason being, even if A is 5 volts and I get 5 volts right here, this diode blocks that effect because it's facing the other direction. So it doesn't matter. It's going to be 0 right there. But if I have 5 volts right here, I'm going to get 5 volts right there. And bingo, bango, bongo, we're giving 5 volts to the resistor. So anything with B high gets us high to the resistor. Anything with A high or A low doesn't even matter. A is just completely useless. It doesn't do anything here. Okay? So let's just recap what we've learned today. All materials have a conduction band of electrons and a valence band of electrons. In which of those bands are the electrons fixed, and in which of those bands do the electrons like to bounce around and freely float? Go ahead and answer. Someone can unmute and say it, or in chat or whatever. Yeah, water cup.
On the valence band. I mean, wait,
Yeah,
I
and
mean
the
conduction band, right? Yeah.
in the valence band they're fixed.
Yeah,
And
so it's the
so there's a bit of
conduction.
confusion about it. Let me go
Yeah.
back.
So it's the
So
conduction
remember,
band, right? Yay. Yay.
yeah,
Yay.
okay. So in the
Yay.
conduction, oh, okay. In the conduction band, they're free to float around, okay? Because in conductors, they're free to float around. In insulators, the electrons are basically stuck in place. We call that the valence band, okay? Now, for do insulators have a big or a small gap between those bands? We call that a band gap. Big, exactly, because it's super hard for electrons to jump from valence, being stuck, to being able to freely float around like they do in conductors. It's a big gap. Conductors, they overlap, so they can just easily move from valence to float around to valence to float around. When we n-dope a semiconductor, are we adding or are we removing free floating electrons? Adding, exactly. And at a p-n junction, here's a bit of a tough question. What prevents the depletion zone from just growing to infinity? Why can't it just grow to the entire size of the p-n junction? So the answer I'm looking for is the electric field in particular. The electric field that exists, once these electrons start flowing, an electric field forms from N to P, and that prevents the depletion zone from further growing. You can look back earlier in the slides for the in-depth explanation as to what's going on there. We're running out of time, so I just want to get it move on. If I attach the plus side of a battery to the P side, what happens to the depletion zone? Can current flow in this situation? So if I attach the plus side to the P side, indeed, the depletion zone gets smaller and current can flow. So here's the attendance code, electric 6. I'll type it in chat as well. And for the course challenge, If you're still confused, go to the help session this evening. Jay and Rena will be happy to help. The link, of course. Can someone else send the link? I just want to show the course challenge. So this is the course challenge. Basically, we give you these restraints, these constraints on your circuit. The more constraints that you meet, the more points you'll get. Okay? But the key is you're only allowed to use resistors that are multiples of 10 of these. So in just the thing is when you make resistors, you can't make them of just arbitrary values. So we can only make them really well in these specific numbers and multiples of 10 of these numbers. So you can only use those values of resistors. They're called E6 series resistors. You can use as many diodes, capacitors, and inductors as you like. And you want to meet as many of these constraints as well as the original design problem as you can. Okay? So this is a very realistic circuit problem. I mean, this is what circuit analysis is like in the real world. You're given some constraints to meet, and you got to design a circuit that meets those. So I think this will be fun. I think you guys will learn a lot from doing this.
Yeah, and just a final reminder: make sure you guys show your work for this, especially for some of the more math intensive ones. For obviously, if you're just doing the single first step, you don't have to write any math. But I'm expecting you guys to show that the power output matches spec and things of that nature.
I will send it out right now so I don't forget. And then we'll make an actual classroom assignment for it.
And remember, 9 p.m. ET, there will be a help session if you're confused about any directions with the assignment, or if you have any questions about the assignment or homework that we've done.
Good. Rena and not Rena Cow have this.
What's up?
Okay. Anyways, we're all
weird thing.
done here.
As late as we'll be able to by ScioCamp is when we try and keep it. But I think a good rule of thumb is have it done by the weekend, end of the weekend before Monday.
Yeah, we're not going to grade it before Sunday. We're too lazy. So
yeah, I'm not going to.
As long as you submit it before we grade it, you're good.
Yeah, exactly. Okay, yeah, you guys are free to go. Thanks guys for coming.
Bye then. Bye.